Let's get to it. I am thrilled to roll out the latest episode of the Quantum Live seminar series dedicated to the research and academic communities. The seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. And I'm delighted to see so many of you coming in from India, Malaysia, Texas, Oregon, and other places. So today I have the pleasure and privilege of hosting Areeya. Hello, Areeya. How are you today?
Hi, Zlatko. I'm good. How are you?
Great. And where are you tuning in from right now?
I'm from Thailand. Right now it's the midnight time.
Well, I'm so glad that you could make the big time zone difference. In fact, I think it's exactly 12 hours.
Yeah, no problem.
On the opposite side of the world. So thank you for that. And I think before we begin with your slides, allow me to give a few minutes of introduction. Areeya is a lecturer at the Department of Physics, Faculty of Science at Mahidol University in Bangkok, Thailand. She's also an adjunct research fellow at the Center for Quantum Dynamics, CQD, at Griffith University with Howard Wiseman. And Areeya did her Ph.D. At the University of Rochester with Andrew Jordan and finished in 2016. And I think I've loved a lot of your work with trajectories and quantum dynamics. So I'm really looking forward to your talk. So I think with that, I can turn it over to you.
Okay. Thank you for the introductions, and also basically really thank you for the invitation. So this is really great opportunity for me to present my work during this time, like the COVID. So it's quite cool. As introductions, I'm from Mahidol University, and today I'm going to talk about the work that is probably mostly quite applicable to the experiments and more application based than many of my talks in the past. So today is gonna be noise parameter estimation, state estimation with a continuous monitoring of quantum systems. So these are the collaborators of these projects that I'm gonna talk about. It's gonna be two projects, kind of separated in two sub-talks, and then hopefully you will enjoy it. And feel free to interrupt with questions. Zlatko will take questions from you. Yeah, so I'm happy to answer the questions on the way. Okay, so as motivation and outline, as I said that mainly my research is based on estimation problem. And then estimation problem could be parameter estimations or noise estimation, state estimation for quantum systems. So we always think of our quantum systems, we always want it to be perfect in perfect environment, but in reality, it's not always like that. We always have parameters that we don't know. We have system states that we always want to know, but we don't completely know what it is. And then we have the environmental noises that is around the systems that affecting the evolution of the system as well. So in order to know the information of this, one would have to do the measurements. So by doing the measurements, we can get information about the system and the parameters of the unknowns. And in general case, these unknowns could be time dependent, so it could change in time. So then we will need something like a continuous monitoring or an estimation of these changing or fluctuating values of the unknowns of the system. So most of my work in the past, and actually is related to many of the estimation theory for quantum system, is that they use a lot of techniques that has been developed for classical systems. For example, classical estimation theory. And then most of my past works related to what Zlatko said, quantum trajectories, which is basically related to classical filtering theory and also quantum smoothing, classical smoothing theory, and then apply to the quantum systems. And I'm not going to talk about this one today, but I think I have mentioned, I gave talks online as well, so you could look at probably Google could help. And then I have talks about this quantum filtering and smoothing for quantum states. And today I'm going to talk about the new things, which is quite exciting for me as well, because this is like the two most recent work that I just got results like in the past few months to a few weeks. And this is like quite, like I say, application based. Hopefully would be fit with like an IBM Qiskit talk. So first one is related to the sequential Monte Carlo in the estimations of quantum system. And then the second one is more like noise estimation using the Bayesian approach. Okay, so this talk is going to be separated in two parts. One is the multiparameter estimation along the quantum trajectories using this called sequential Monte Carlo method. And I'm going to apply to the experiments on superconducting qubits for Transmon in the 3D cavity. And then the second part is going to be the optimal protocol for the spectator qubit. So this is like a new way that we propose to do the noise cancellation using the spectator system. Okay, so let's start from the first one. So this is the multiparameter estimation, and this is the collaborators for this project. So the idea of using the SMC basically comes from Jason Raff, professor at the University of Liverpool. And then so he had these papers on like SMC for quantum trajectories already in 2017, and he was like interested in applying it to an experiment data. And so he like contacted me, and then I kind of like connect him with like the experimental people who I have been working with through during my PhD, and then we get the data from them, and then so we process this together. And I worked with Howard Weissman as well, and this is like Natapong from my students at Mahidol University. So this is the three experimentalists, Kater and Marty and Steve. Okay, so what is the sequential Monte Carlo method? Is a technique that has been used in signal processing, tracking, and control, and finance and robotics and etc. So it has been used in the classical estimation theory already, but now we're gonna use it for the quantum system. So what is the sequential means? It's a sequential version of Monte Carlo method. So I think everyone knows what the Monte Carlo method is to do the simulations of like random points or the, generating the random points depending on the probability or the true probability here, and then using as the like representatives of the probabilities that you can find the mean or the variance or the covariance from these points here. And then we're going to apply to something that is more like the time dynamic, where this is the pictures of the Markov model of nonlinear time series model with a hidden set X and the observations Y. So this is like in it's like a time dynamics of X, and then with the different times, we also have the observations of the states X here, which is unknown, and then Y, which is known to us. And then there is a dynamics is governed by some function F, which connects the xt at different time, and then the function G, which connects the measurement record with the state.
And quick question, nonlinear here in the sense that X and Y are related in a nonlinear way?
Yeah, it could be nonlinear, that's right.
Yeah.
Okay.
And this is maybe just a more general question from another recent discussion we had, but you know, when you do this sampling, say with Monte Carlo and so on, in this nice picture here, you have the probability density function. You know, there are a few regions which have some interesting features, but are very small in probability. They're pretty rare. So you're kind of likely to miss them if you equally sample. So is there some thoughts on that, or like do people worry about that? And
that's going to be the next page.
Oh,
that's right.
Wow, okay, so, great segue.
That's a good question. So as Zlatko say, that there are a lot of problems with like sometimes there's some area, excuse me, some area that is really low probabilities that you would really likely missing the probability at that area. And so there are a lot of techniques that has been developed in order to fix that problem. So here I'm comparing, so that is the problem of Monte Carlo by itself. It's not related to the sequential. Sequential is just the next step of the Monte Carlo. So even though Monte Carlo itself, it has that problem. So here's the way to fix it, is to use something called the instrument in distribution. So let's start from like the true mean. So this is the true means that you want to find. Let's say that we have a function of x that you want to find the mean, and then the p of x is the probability distributions of the unknown x. And then this is the way that if you know the exact form of the h, then you can just do the integral and then you get the mean. But let's say that you want to do the Monte Carlo way of doing the samplings. So if the p, or the probability distribution function, it's quite nice, then you can just do the random sampling with the true probability, and then get the different values of x. So C here is an I. I'm using this I as the particle. It's just like it is just a term that comes from like classical literatures that they used to call it particle. So it's just a sample point, and so this x is sample from this p. And then you can calculate the h function. And then if you sample it with the correct probability, you can just summing it over and then divide it by n. And that's how you can get the mean, right? But now if that probability is really hard to do, or has like a long tail or something like that, then people fix it with using this instrument distribution Q, which is easier to do the simulation with. For example, Q could just be something close to like uniform distribution or something like that. It could be the uniform distribution as well. And then how can you get the correct mean is to do the corrections onto it by this particular thing, which is called like weight. And the weight would just be the ratio of, so you can evaluate this weight by using the ratio of this probability, the true probability, with that instrument probability. And then so this way would kind of help solving the problems that Zlatko probably you raise that up, and then you can get a better accuracies of the mean using that n particles, like finite particles n.
And how do you go about selecting Q of x, the instrument distribution?
Yes. That is like I don't think there is. I mean, I don't think there's the best or optimal way to fix the Q. Mostly, Q would just be something that is like nice and smooth. It could start with the uniform distribution if you don't know anything. It could be something that is like a Gaussian distribution around the place that you think it is dominant, and things like that. So it really depends on the problems that you're interested in.
This, I don't know much about this, but it sounds to me a lot like importance sampling as well.
Ostensible, yeah.
Sorry?
Right. Is that you say ostensible?
I said importance sampling.
Importance sampling. Yes,
Yeah.
That's another name. So I've been reading the literature. So this Q, comes with a lot of names. So this is just one name, instrument distribution. Another name is the importance probability or importance distribution. And then in my work so far with like Howard Weizmann, we have been using another terms called ostensible probability. So they are like all having the names, but they basically just the same or similar quantity. Yeah.
Okay, so they're pretty much interchangeable.
Yeah. Mm-hmm. Right. So so that's good. So did I answer your questions? Yep.
Yeah, so I guess to kind of come back to the picture you had on the previous slide, to put a picture to the equations here, you know, in this true PDF function you have, let's say that we have some a priori knowledge and know that, you know, at that little tiny bump on the top there, we kind of know that behind there, we know that that's a some importance in the very low part of it. So we might pick a distribution that isn't quite even in our sampling, but has maybe a Gaussian to exaggerate that, to amplify that.
Right. But if we don't want to miss all these points, like the little bumps here, so we want to make sure that the prior distributions or the Q distributions also cover this area as well.
Yeah, so the Q distribution would be taller around the little bumps and less tall bumps.
Yeah. That's right. Oh, good.
Awesome, thank you.
Okay, so now let's like switch to the sequential one. Well, the sequential one is just more like adding the like this picture into the picture of the Monte Carlo, because now we have the observations onto it. So you can think of this one as now the h is the function of the time dependent function, which is like an x from 0 to t, and this pi is just the probability of that trajectories of x from 0 to t, and then it's conditioned on the observation from same time, like 0 to t. And then this is the same way, if you can sampling the trajectories with the correct probability, you can just do the sum and then divide it by the n. But then otherwise, you could do it with the instrument distribution, the importance distributions, and then get the same average using the weight, which is the ratio of the true probability divided by the Q. So the next one is like, how can we choose a Q? And that's the question. And then how can we relate this to the quantum trajectories approach? And that's the idea. So yeah, questions? Or
and is Q going to be fixed for the whole experiment, or is it potentially also?
No, it's gonna change. So for this one, it's gonna change with the Y. It's gonna be updated every time that you get a new data.
I see.
Into the problem. Yeah. Okay, so just a little bit of introduction. So Zlatko probably know all of this, but then for like some audience that might have maybe just a little bit of review on the quantum trajectories, is the theories that work with the system that couple to the bath. Basically, it is the open quantum system, and then with the open quantum systems, if you like the system interact with the bath, and then we have no idea what is the bath is doing or what the state of the bath is, then we would just do the tracing over the bath, and then the result is just the Lindblad equation, which is in this form. Some part of the Lindblad would be like unitary evolutions, and then some part of it is a non-unitary, which is in terms of this operator D here. And then with the strong Markov assumptions, then the bath could be measured repeatedly on a time scale that is shorter compared to the system evolution. So with this monitoring, then one could get like a stochastic record, which is in terms of this Y here. So this Y would be depending on the observable of the systems that you're interested in, basically the part that is interact with the bath that you can measure. So it is an expectation of this C plus C dagger here, which is the Lindblad operator. And then, so let's say that if you want to do, if the system is coupled to the bath via the sigma SAT operator, then this one would be sigma SAT expectation, which is just the SAT coordinate of the qubit. And then it has a noisy part, which is like the Wiener process of it. So this is the measurement record of this form. So once we have this measurement record, we can now get a better information about the system. It's not just evolving like with this where you just trace out everything. Then this one would become something that's conditioned on the measurement result. And this is called stochastic master equation, which I will call it SME, which is different from SMC. And this is the evolution of stochastic master equation, which has the terms that is similar to the master equation above, and then the second term and extra term, which depends on the measurement result, which in this case is just a part of the Wiener process here. And then this condition state is a function of the past measurement record. Means that like if you have the if you want to compute a state at this point in time, then it is a function of the whole record in the past. to get the state at that point. So this is a part of doing the quantum trajectory where you can get like the measurement record here, and then you can calculate the quantum trajectory from the initial state and evolution to some time tau. Okay, so one point that I want to show you that is that this one is telling you how the state is mapping in time depending on the measurement record. So like if you have like some measurement record here, then you can calculate the rho at the next time step using this equation. And this is just a 2 example of the quantum trajectories for superconducting qubit experiment. Okay, yeah.
And maybe just a quick comment that this form of the SME is for the particular type of homodyne unraveling, but you could have.
That's right. Yes. I am focusing on the particular part that is like diffusive measurement, which is the measurement recorded in terms of the Wiener process. And actually, yes, because you are working on the jump, there is another kinds of the SME, which also continuous monitoring, but it's monitor instead of the homodyne or heterodyne, it monitors the quantum jump, like you would get click or not click. And then the part DW here would just depends on the N, or like whether like just 0 and 1, basically. And that is just the quantum jump SME. Okay, that sounds good. So, yep, so this one, in this work, I was just focusing more on the diffusive part of it, and then because the measurement is kind of the weak measurement and continuous as well. So this is just a picture of like kind of the pictures that I like, more like explaining the quantum trajectories, because you can see that the evolution of systems in time, and then at different time. This is like a Markov assumptions where the system interact with a new path every time, and then it get detected and get the outcome, and then the new path comes in and interact with the systems and so on. And then so this like dy 1, 2, 3, 4 here is just the measurement records that we get from the experiment. And then using that dy, we can get the state of the rho, which will combine and then get the quantum trajectory. And then in this case, we can get the evolutions of rho if you know all the parameters of the system, right? So like in most of the experiments, we will try to get these parameters first, and then calculate how the state is moving time. So now assume that like these parameters are unknown, or we have no idea what it is, then how can we use these SMC, which is like sequential Monte Carlo, to do the estimation for us? So the idea is to start with something that is basically we just sampling all possible values of lambda. So in this case, it's just an example of like two-dimensional value of lambda, and then this is just like random points. Basically, it's not really coming from any correct probability. This is just for explaining the idea. And then so this is like particles, and then at the beginning I would just put weights on it, which is like a simple weight, like an equal weight 1/n. And then for the next steps, then I get the measurement outcome from the measurement, the records dy, let's say at time k, and then I can calculate using the SME, which is the equation for the state dynamics that I show you in the previous slide, to get the rho at the next time step. So you see that there's an I here, because this one is just like kind of trajectory for each particle, which means that it's a trajectory for each possible value of lambda. And then so you will get trajectories from here. And then from this, we can calculate the probability of the measurement record, given that the parameter is that lambda I, and then the state before that is also like rho at I. And then we can use this thing to update the weight. This is like related to the questions of like how can we like choosing the Q or choosing the no, we don't choose the P, we choose the Q. So in this case, we choose Q to be something that is like related to the probability of the measurement record, because it's something that we can calculate from the dynamic of the quantum trajectory, and that's just an easy way to get it. oops, sorry. And then so we choose this one as kind of the Q for us, and then we can update the weight using this probability of the Y here. So this process would just keep repeating every time step again and again and again until you like ran out of the record. And most of the time, like if like one measurement record from like time 0 to time t, if the information of the parameter is not enough, then we just have to do it again for like another different records, another run of the experiment until you get a good accuracy of the parameter. And then there also like the resampling part, which I'm not going to talk about it into detail because there's a related to how things get like, let's say that some parameters just get narrowed down into like a few, or the weight just kind of get narrowed down into a few of the points. Then you will need to do the resampling because then you want to be able to kind of explore as much as the value of possible parameters as possible, and so that you don't miss or like go into like the non what was that called, like local optimal points. So there are a lot of techniques inside here, which I will just refer to the paper Jason 2017. So this part is the part that I'm gonna apply that technique of SMC into the quantum trajectory approach and also the experimental data. So this data basically comes from the experiment from Siddiqui groups in Berkeley. And then so they work with the Transmon in the 3D cavity with the LJPA, which is like more like just amplifying the signal. And then so the idea is that they work in the dispersive regime where this is the cavity input coupled to the Transmon qubit, and then the phase would get shifted depending on the state Z, or basically the up and the excited and ground state of the qubit. And then one can get a detected signal, which comes from the homodized signal on the X2 quadrature. So this is just like the voltage signal that we can read from the detector. So this is the two example of the trajectories. Like one is like with just the measurements, and then you can see that it collapsed to X or Z equal to 1. And then for this one, it's when the Z measurement is going on at the same time as the Rabi oscillation. So you can see that the Z and the X value can kind of like doing the oscillation with the fluctuation on top of it. So how can we get this trajectory is we had to do, or they had to do the calibrations of all the parameters that need in the model. For example, like this is the equations that explain that quantum trajectories. It has the Rabi oscillation with the omega as the Rabi frequency, and then all the measurement rate, and then the measurement efficiency, and then like T1 value for the qubit, and so on. So all these parameters has to be done, well, kind of determined from like independent calibrations. And so you can get some numbers and then you assume that it will just stay constant throughout your experiments, and then just put in this number to calculate the quantum trajectories.
Quick question.
Yes.
Yeah, I'm a little, can you help me understand why there's an, is this an efficiency eta inside the L hat jump operator that also goes in the Lindbladian?
Yeah. So let me think.
I would have only expected it.
Okay. I see. Yes. So this is just like the way that we we define things. So it doesn't have so the tau. So the tau is like kind of measuring the measurement time. It means that how long you would need to integrate the measurement signal in order to get well, like one signal to noise ratio, and that's the time scale of the measurement that we use in this definition of tau. And so in the tau itself will also depends on the eta. So if you have like different ways of defining things, the eta would just cancel, and then the eta would just be in front of this function h here. But the reason that we define it this way, because we can say that this tau is actually telling us how long you should integrate in order to get like signal to noise ratio to be 1.
Mm-hmm.
Yeah. which also depends on the value of eta, right? Like if eta is too small, then you need to integrate it longer or something like that. Yeah. So it's just like our convention. Yeah. But thank you for asking. That's a good question. So so with these, you can see that lots of parameters here that in the model, and in order to calculate these, they in experimentalists just do the calibrations to come up with these numbers, and then me as a theorist, I would just use it and then calculate the trajectories, and then they would just compare with the tomography data. It's a perfect agreement. Okay,
and,
but
two quick questions. So in dy t equals vt minus v0, is v0, what's v0?
Okay, so v0 is like a bias, or basically like kind of like an offset signal. So
like the DC level, or
the what? Sorry.
The DC the DC level, the zero frequency level.
Yes. That's right. Yeah, and this is something that you will see. It is actually playing a role when we do the SMC on the measurement signal itself. So my point is that like in order to get the trajectories, we in the past we had to do like different experiment, like a separate experiment, to get these numbers out, and then use this number to like assume that it will just stay constant when you do another experiment, and then getting the measurement signal, and then we can use these parameters to calculate the trajectories, right? But it turns out that what happened is, so in the SMC, okay, I'm not sure, I'm just jumping too far. It's an SMC is that you can just getting the measurement readout. You don't have to do the calibrations. Just give me like the raw data and some model that you think that your system is behaving, and all parameters that you think it is could be non-zero, and then just give it to the SMC and let the SMC run on that signal directly. And
that's really cool.
So this is what we found. So we had to do it on like 200,000 individual records, because the thing is like this measurement is quite a weak measurement, like weak but continuous. So the information from like one single record at like 1 microsecond or 2 microseconds is quite small, and so we had to do quite a lot of data on that. And also because of the noise is quite like not informative, we have to do an average of the noise in block. So in this case, we just do it with like 512 records, which is just like really a random number. We kind of play around with the number of different records, and then see how much information that it's kind of stored in one record. So we found that 500 is around like quite a good number. And so we kind of separate the record into like this 500 chunk, and then this is the plot onto the number of blocks. So one block is 512 records, and then so if you think of it, like one measurement record is around in this picture is like 1.6 microsecond, and then usually in the experiment you just keep running, right? You don't do it like 1 microsecond and stop. You just like keep most of the experiment just like keep running, and then you would just collect the records in order. And so this one is to show that the parameter that we found is actually drifting in time. Some of them, it's actually not so much of the drift, it's kind of constant. For example, this one is the Rabi oscillation. So the blue one is the estimated values from the SMC, and the green one is the original value that comes from the independent calibration. And then the red one is the average of this blue one, basically. So you can see that they are really close. In basically it's inside the error bar, and then gamma, which is the decay rate, is around the same. The value of eta is around the same as well, and T1 is like 0. It's almost approximately 0 for Transmon. And then this one, this is like a different things. This is like what Zlatko asks, like what it is. It's like the offset voltage at zero frequency. Zero frequency, and so the original value is like 1.5, and that's the estimate from the calibration. But what we found is that it has a shift in time. And if you cannot see it, we have like the zoom in this picture that the bias voltage is actually starting at constant at one point, and then it start to shift at maybe around 150, which is like an order of I think it's 100 millisecond. So this is like a time scale of the shift in the bias of the measurement. And so this is what we found from the SMC, is that the values that we get from the calibrations is actually not representing what is actually going on inside the experiment. Okay, so this is kind of the cool idea of like processing the data directly instead of doing the calibrations. And then so we're gonna play around with different data. So now we are currently working on for fluorescent qubits as well. And if you guys at IBM, if you have some data for us to play, please just reach out, and then we can work on this together. So hopefully it would be useful in the future. Yeah.
It's very cool. And how do you estimate the error bars here?
The error bars is just coming from, like if you go back to this one, it's related to the weights of like different parameters. So the estimator would just be the mean, and then the error bar is just gonna comes from the variance of like this weight of the parameters.
Gotcha. Okay, yeah.
Yeah, which can be updated. So the variance could be updated depending on how much data that it can. But in this case, you can see that the error bar is like at different points. It's just because like we separate the data into like block, and then one block will get one estimate, another block will get another estimate, and so on.
Mm-hmm.
Yeah.
It's from the collection of lambdas that you have that you just directly pull it. I got it.
Right. Yes. Mm-hmm. Okay, so cool. All right, so that's actually the first part. Hopefully the next part is not going to be too long.
Thank you.
But I think this is going to shift the gear into like whole different regime, but I think it's also exciting as well. And this is like new techniques that we just found, and hopefully it would be an interesting directions for like noise canceling. So this is related to the noise canceling project between Australia and the US, actually, which is called like Osmary project, and they basically trying to work on like kind of investigating how can we get any better noise canceling from using this spectator system. So what is a spectator system? The idea is so you have like something like called like a data qubit, or something that you want to do the computation on, and you don't want it to have an effect of like noise or the errors on it. And then there are a lot of protocols like dynamical decouplings or like quantum error corrections to try to keep the quantum information untouched or like intact. But then for us, we proposed a new idea of why not we just trying to let's find a frame of it, which is like sitting right next to it, that can probe the noise for the data qubit. And then this is the part that we can kind of probe it as strong as we want. You could do weak measurement on it, strong measurement on it. You could do as fast probe. You could do control on it as well. And then hopefully we can get the data from these spectator systems to be able to help correcting the noise that affecting the data system. So this is the idea of the spectator systems, and this is the projects that has been involving a lot of university in the world, and this is probably the first worked on the project or on the program, which is like from the US actually, which is like looking at the calibrations of the noise from the magnetic field using the spectator qubits on the side of it. And this is like on the trap ion. So more like theory, I think. This is not an experiment yet. Okay, so in this work, which is like my part, is to look at the noise estimation on the single qubit first. Okay, so the motivation for using spectator system is, first of all, it will avoid measuring the data qubit. So like the data sorry, I'm just like data and data. It's switched between the Australian and US accent. Sorry about that. But so the data qubit is something that we don't want to touch so much. And so we want it to be separated from us, and we don't want to measure. We don't want the noise to be affecting it. And then so the idea of having the spectator's qubit is to be the one that will read out the noise, and then we could do the measurement on it. So this one would just make us kind of avoid touching the data qubit as much as we can. And actually we can do the correction on it, but it could be much slower rate than the error rate. Another key point is that it does not require many physical qubits for the error correction. And then we know that in the error correction, we need to make like many physical qubits in order to do the error correction code. So in this one, in theory, we would say that we could just at least like as low as 1 qubit per one type of noise, for example. So compared to the dynamical decoupling, it would just like, we don't need to do the control on the data qubit, and then it doesn't have to be so fast, because in the DD scenario, one would need to do the control on the qubit in a much faster rate than the error rate in order to correct the noise affecting the system. So this is the protocols that we look at with the noise realization. And then we have the spectator qubits that hopefully can track the noise. Basically, it can be more sensitive to the noise than the system part. And then it can evolve in time and can track the noise in time. And then our questions that we want to ask is like, what's the best strategy that we could do when we could measure, and then how we can do the measurement in order to get the information about the noise in order to correct whatever the noise that's affecting the system. So that's the main question for our project. And we just look at a single qubit, and it turns out it's not a trivial problem at all. And that's why we're just going to look at like single qubit right now. There's just one data single qubit and one spectator qubit. So this is a regime that we are looking at. Let's try with the noise that is like quite a simple noise, random telegraph noise, just like switching between 1 and -1. This one is an idea that comes from like a solid state system, where they could be like a charge noise, like the electrons just jump in and out from the substrate and so on. It basically kind of replicate the random telegraph noise in the solid state system. And so we can use this in here with a jump rate gamma up and gamma down, which doesn't have to be the same. And this is the pictures of the 2 qubits, the data qubit, which is like D here, and then the phi S would be the phase of the spectator qubit. And this is the Hamiltonian of these 2 qubits. So this is just like a really simple phase of the 2 qubits. One is like rotated with the rate kappa D, and another one is rotated with rate kappa S. And then the rate would depend on the beta, the angle would depend on the beta, because beta would just be like positive and negative, right? And then if like beta becomes 1 all the time, then the X, which is like accumulated noise, would just be equal to T. And then if it is -1, it will be just equal to like minus T. But if it's flipped between back like plus and minus, then it would just be an accumulated noise. And so the phi, or the angle, would just be kappa D times X, and this one would be like kappa S times X, and so on. And this one is the measurement that can be applied onto the spectator qubit. So we just use like a really simple one for now, which is like the polymetrics measurement onto the qubit, which is like measuring the theta angle, like basically polymetrics at the angle theta. And then the outcome would just be like 1 or 0. So this is like a strong measurement, but continuous in the way that you could just do the measurement at any time. You could do it now or later, or like wait a little bit longer, and so on. Okay, so this is the useful regimes that we're interested in. Definitely we want the kappa S to be larger than kappa D. This is like what we want, is that we want the spectator to be more sensitive to the noise. And then gamma rate is the jump rate could be anywhere in between. And definitely we want to measure it faster than the rate of the gamma. And this one is just to say that the kappa S, which is the measurement rate on the kappa, or the sensitive rate or the rotation rate of the spectator qubit would just be faster than the rate of the time of the total time. Okay, so now how can we all do of this math, which is like all these components going on? There's a lot of parameters to be estimated, lots of parameters to be optimized. For example, like the measurement time, it can be anywhere, like T1, T2, T3, until final time. And this is just the waiting time, which is like difference between the two measurements. And then the measurement angle could be anything as well. It could be like theta 1 until theta n. So it depends on, we have like n measurement, would just be the n numbers of theta. And then the measurement result will be something that we get from the measurement. And then the value of noise beta would just, I use like beta 1, beta 2 here. It just means that beta at the time tj. Okay, and then the accumulated noise, which is like defined by x, is just that x at time t2 in this case. So x at time t2 is just the integrator of beta from t0 to t2. So this is all the parameters that we have to play with. And then in order to solve these, so we start with like a Bayesian inference approach. So we have to look at what probability of the beta, which is like probability of the noise in the beginning, and then at the time t0. And then next steps, then we can calculate solving the RTP, which is like random telegraph noise. So it's just like solving the Markov chain with the rate gamma up and gamma down. We can get the probability of beta at time t1 and then x at time t1 given the beta at time 0. And then multiply with the probability of the measurement record at that time, which is probability of R. And this probability will be dependent on the accumulated noise at that time, right? Because it depends on the spectator qubit, because the probability of the measurement record will depends on what is the value of phi s that is different from the theta, right? So this one will depends on the x1 and also depends on theta 1, and also depends on the time, delta t1 as well. And then the process will just keep repeated with like the Bayesian inference with the next time steps and the third time step and so on. And then you could go on to like n time steps. And this is just gonna be the form of the probability multiplying this together. It's just the probability of beta and R and X as well. And then in order to get something that we want, which is like the probability of the final X, which is going to tell us the phase of the qubit at the final time. And then we can find the conditional probability of this by just doing the normalized factor n here. And then also we need to do summing over all the noise realization, because the beta is something that we don't know. So we just have to like summing over all the beta as well. Okay. So hopefully this kind of makes sense. It looks quite scary. And the next grade is probably, okay, less scary, but we'll get there. Okay.
Could you quickly remind us how you measure, how you obtain theta?
How we obtain the theta. So theta right now is still the variable that we want to optimize. And that's going to be the big problem later on. Like, so we're going to find a way to find what's the base value of theta that will give like the best protocol for us.
Okay, yeah.
Yes. Mm-hmm.
Oh, okay, that's yeah. Okay, so measurement angles. This is the thing that you want to estimate.
Yes, and also, well, not really estimate. So we kind of estimating the phase of the data qubit. That's the main goal. But this is a variable that we can play around with. So we want to find the measurement angle that will give the best estimation. Yeah.
Yeah.
And then I think the next one was going to be useful to answer that question is like, how do we know what it means by best, right? And then so we need to first like define the optimality conditions. So these optimality conditions is just gonna be divided by the cost function, and then I will just define the cost function based on what we want, right? Because it's the phase of the data qubit, which is like what kappa d times dx. Okay, so excuse me. So this one is just the true value of the phi d, let's say, and this is the estimator of the d. So we want these two to be the same, right? Like as much as we want. And then we can define the cost function. Usually people would go with like the mean square error, but for this one, which is like the periodic function, I think it makes more sense to define it in terms of the exponential or like with the I, which is like more like a phase. And so the good thing of this term is that, so when they are the same, right, you will get 1, and then the lowest value is just 0. So it's really not a cost function. I'm going to call it reward function because it's more like we want to maximize it. But the cool thing of this definition is that, let's say that at the end of the measurements at time t, and then you come up with the estimator, like phi d, the check, and then what you do is like, okay, that's my base estimates of phi. I'm going to do the correction because I know that like the phase phi d is the angle that is moving with the noise. And so I'm just going to correct it with that phi d backward, right? And then so this thing with the expectation value is just the average coherence of the data qubit at the end of that time. So so this is like the way that we want to optimize. And then so this basically we just optimize like the least decoherence or like the most coherence of the qubit at the time t. Okay, so this one is well, one can just calculate it directly, straightforwardly, if one knows the probability of the phi d condition on all the measurement records here, and then with the exponential in between and do the integral, right? And then with this cost function, we can find, like maximize it, and then find that the optimal estimator is just equal to that part on the right here. It's just the integral of the exponential phi d. Okay, and it turns out that with these things, we can replace that one in the equations, and we find that these reward functions that we want is just the absolute value of this integral here with the probability of phi d. And then we know that phi d is just equal to like kappa d times xt, and then in the previous page here, we have the probability of xt in hand already, and that's what we're going to use it in the calculations. And that's what I'm going to call the R function, which is like the reward functions that we want to maximize. Okay, so this is going to be quite a scary page, but I know that like this is like skipping 3 pages of calculations already. So so stay with me. So that's the functions of R that we want to calculate it. And you remember that I show you all the Bayesian probability, which is the multiplications of all the functions of R and X here, and with the exponential here. And it turns out that with the convolution techniques and a lot of like convolution integrals, it turns out that I can just simplify these equations into the matrix multiplication. And it's really simple, just becomes this term here. It's just like the vector of A with 2 elements, the complex numbers. And then this one, it just means to add up the elements of that vector together. And then find the absolute value. And this will give me the value of the reward functions already. And then how can I get this AN? It would depend on these all measurements here. That is what I said, which is like 1 and 2 and 3 and 4 and so on. So it just becomes the matrix multiplications where the A is the 2 by 1 vector like this. And then it also represents the probability of beta at 0 time when you haven't done anything. And then multiply with the F, which is like the 2 by 2 matrix, which I will skip the form of F, which is quite complicated, but it's related to the measurement at that time, it depends on the measurement angle theta 1, and it depends on the measurement time t delta t1, and also the measurement result r1 as well. And then when you do the next measurement, you just basically multiply the f together until the final time n here. And then you will get the an at the end, and then summing over the elements to get the reward function. A little bit on the normalized factor is that it also can be done in a different, in a similar way. And this is the same normalized the factors that I showed you earlier, just to kind of make things complete here. Okay, there's a lot of faith in here because there's a lot of like details that I have to skip because it's gonna bore everyone with like math. But hopefully the next step is gonna be less. So once we have this like really simple protocol of like mapping, so we call it, this one is like map-based optimized algorithm, is that we can just do the matrix multiplication. So here we start with the A0, which I said that's related to the probability of beta or the noise at the initial time. And we just assume that, let's say that at that time, the noise is already in a steady state at some point, right? And then so we can just use the probability of the RTP. So you probably have seen this one before. This is like the rate, or well, the probability of the beta being +1, and this one is like probability of beta being -1 in the steady state. And then for the next measurement, you just multiply the f onto the a with the two value of r, because like r could be 0 and 1, where the setting is like theta 1 and delta t1. And then the next measurements, you apply it again, and then you get another measurement outcome 0 and 1 here. And so it becomes like 4. So it starts from 1 and goes to 2, and then go to 4 possible outcomes. So this one is like, you can kind of like calculate all possible trajectories that could be happenings. And this is just the, oh, okay. So I have to say that because A is the 2x1 vectors and it has the complex number, but it only have 2 degrees of freedom. So we want to be able to kind of represent it in the graph. And so we came up with the way to define the 2 real number called alpha and theta in this way. So it's just like the ratio of the one elements that related to the beta plus, and then the beta minus, and then finally the argument. And this one is just the absolute value of the difference, and then the sum of the absolute value. Okay, so there are like interpretations of this value as well. So I'm just gonna skip what it is right now because it's quite complicated. But the interpretations of this theta is related to the likelihood of the beta, because somehow like this from these formulas here, it turns out that the value of theta is telling you that if it is positive, it means that at that time the beta would be more likely to be +1, and if it is like the value is negative, then it means that it's more likely to be in the -1 state. And then so this one is just like to show an example. It's not much more than that. Is that I start with like this one, the starting point t0. Sorry, this has to be t0. It has 1 point here, which calculated from the steady state of the beta, and then it jumped to 2 possible outcome, and then it jumped to 4, the red dot here, and then it jumped to 8, and so on. So it kind of go everywhere. But the interesting thing is when you look at the defacing rate, it's actually better. So this is the numbers of the time of the measurement, which I can just like kind of put like really random numbers in there. And then the measurement angle could be just random as well. So this is like related to the questions of Zlatko. It's like, okay, what's the value of theta? I can just pick it randomly, but at the next time step, I will do the optimization to find the optimal angle later on. This is just to show that even if I like pick it random, so this is the parameters here, I get a better decoherence rate, well, like lower decoherence rate on the qubit already. So this is a compare with like no measurements at all. So this is basically the exponential decay with like kappa square over 2 gamma, which like anyone can calculate it with the RTP noise. And then this one I'm plotting 1 minus of the coherence of it, and then so that I can define it as a cost function as like 1 minus r. So this is like the one without the measurements, and this one is with the measurements at like time 0.8 here, and then at 1, and then at 1.5, and then at 2.8. This is quite random, and then the measurement angle is defined by there. So you can see that with the measurements, it's already help in terms of like the coherence of the qubit, because basically you get more information about the systems, and then you can correct the qubit, and then you can get like less decoherence. So you can see that another thing that I think it's interesting is that this t. So if you make the first t to be infinitely long, just for fun, I would just get back this line here, because that means like there's no measurement during that time. So this is just to tell us that like just one measurement is already better than no measurement at all. Okay. All right, so now let's go into how to do this optimal protocol. I have the variables. I have a lot of variables to optimize, but in order to do something like doable, I have to do some approximation on it. And so our approximation goes with something that is quite normal. For example, we want to approximate that the switching rate of the error is slow enough. And so that means at that time, at some particular time, this is a spectator qubit. So the spectator qubit will start from 0, and then it would just rotate depending on the value of beta. If the beta is equal to +1, it would just rotate it in the positive directions, and if it is -1, it will rotate in the negative directions. And then the question is like at some time dt, which is small enough than the switching time of the noise, then we can approximate that the value of theta would just be equal to kappa h times dt. Because like beta doesn't change, the beta would just fix either like positive or negative. It hasn't been shifted yet. And so this is the approximation. And then now the next question is, if that is the case, then what would be the possible angle that we want to measure? And the answer is like coming from the state discrimination theory, where like if you have like the two states here, and then you want to discriminate between one or the other, what would be the best measurement? And then the answer is like, if you have no idea, like if it is like 50% on up and down, then the best angle would be pi on 2, which means that this angle is like along the y-axis here, because then you can get the information about like top one and the bottom one. But then if you have some information of like, it's more likely to be positive beta than like negative theta, then the base angle would be equal to the phi s here. So basically the angle of the measurement should be somewhere approximately plus or minus kappa s times delta t, which is like from this approximation there over here. Okay, so this is like the things that we're going to use in our protocols to make the analytical calculation easier, and also the simulation as well, is that we will use these non-adaptive and adaptive regime. So for the non-adaptive, it just means that, well, the angle, I would just pick it along the line of phi s, but then the sign would just be positive all the time. But for the adaptive one, is that I would just switch the sign depending on my sign of zeta, which is why I already mentioned that zeta is kind of telling us the likelihood of beta, of positive and negative. And so in this case, should be better, right? Because you can kind of like changing the sign of the theta depending on the sign of zeta as well. Like you can kind of like, you kind of know that it should go in this way, so let's just measuring in that direction. And if it goes to the negative one, you're just measuring in the negative direction instead. And so this is the protocols of us like looking at this page of like This is like noise, which is the red line here, switching back and forth. And then this one is the spectator qubit, which is like, I think I probably forgot to say that our spectator qubit has to be resetted every time that it get measured, because just to make it easier. Like, you don't want to keep it rotated because you have the control on it. So once we do the measurement, we can just reset it to 0 and then let it measure the next time. And so this is a part of like resetting the spectator qubit to be 0, and then it collects the phase, and then we do the measurement at this point, and then collect the phase and do measurement at this point again. And then so the measurement time would be the same at every time for this case, right? Because we say that there is a correlation between the time and the theta. So we want them to be the same. And so in this case, we're just gonna make it equal, like equal waiting time for now. And this one is a data qubit here in the green line, and this one is the measurement records that we could get like 0 or 1 or 0 and so on. And then from this data, then we can calculate the phase of the data qubit and then do the correction on it. And that's the idea. Okay, so with that adaptive and non-adaptive regime, it turns out that things are quite nice, and it can be something that we can calculate quite easily. So with the map-based algorithms that we have, now we have the word adaptive in the algorithms in here. So this is a picture of the scatter points on like zeta and alpha that I show you about. Like, it maps from like 1 to 2, 2 to 4, and 4 to 8, and so on. And this one, I did it for 10 times. And so at the end, it has like 1,024 possible choices of all possible measurement record. So it's nice that you can kind of see that all the 1,000 points just kind of clumped into like a few points on the scatter plot. So it's quite an interesting features here. So this is for non-adaptive, and this is for the adaptive one, which is like, you kind of expect it to be symmetric, because you can see that we changed the angle to be depending on the value of zeta. So it's kind of keep it symmetric in the problem. And this one is the decay rate. So the decay rate is much lower, much lower than before, where the adaptive one is actually better than the non-adaptive case. And this one is the scatter plot that will tell us that somehow it has some kind of like interesting features of like all these 1,000 points will just like clumps into just 6 points on this space of like alpha and zeta. So then that's when we found that, well, it's possible that we can try to find the angle that is optimal, because this one is just like a really like random angle, like 0.4 pi here. And then we change the angle, and then we can kind of see the same pattern. And that is the reason why we get to the last point for us, is like we get into the point of asymptotic regime. Means that we find that like the more that we keep the measuring it, it's the point would just like stay in this like kind of the stable regions. Like in this case, it's just like 6 points, and then it's also the same with different angles of data as well. And then we look into it on how the point is moving. So let's say that it starts from like state here, and then what's the outcome that will move to that point, and then it will move to that point, and will jump down to here, and so on. And then we can map this one, which is like quite a general, like a Markov, hidden Markov model in some sense. But this is just like the map of the states of the noise, in the sense that it goes from one point to another with like different metrics. So if you remember now, like I have points on this plot here, but one point on this plot is just like the vector A, which is like the vector that we interested in. And then each vector would just be mapped with the metrics every time that you do the measurement on it, right? So in this case, like if I stay here at the value of A, and then I do the measurement with the positive angle here as an F plus, and then I get an outcome 0, I would just go back to the same point. But if I do the same measurement, F plus, but I get an outcome 1, my state would just jump down to here. And if I do another measurement with like a negative angle, then and I get 0 outcome, then I would jump to here, and so on. So this one is like a really like a general form that we found from looking at different patterns of the maps. And then we looked at the probability, which is going to be related to the asymptotic regime. It turns out that if you waited long enough, well, long enough, it just means like 5 measurements, actually. It's not that long. So 5 measurements, by 5 measurements, like the plot or most of the probability or like population would just stay in just like these 2 things where you can see that there is like some kind of the remap into the same point. And then we find that then we can calculate things from just these stable point, these 2 points here, and then forget about the rest because there's not much of the probability that will stay in those states. And then if you like heard about like chaotic regimes or mapping problems, then we would think about the eigenstate of the matrix. And that's the way that we go with like finding the eigenstate of these 2 most probable matrix or the states here, which is like F plus 0 and F minus 0. And then finding the eigenstate of it, which will represent that state A here and then state A there. And then we can use just that too to calculate the measurement rate, sorry, the decoherence rate for that particular angle. Okay, so almost there. This is the part of the calculations of the decoherence rate. This is like something probably more familiar to use, like one dot with like some A before it was an A. But in this case, we just look at just a stable eigenvector of the 2 states here. And then this one is minus with some the same state, but let's say that you do another measurement on top of it, and then summing over all the possible outcome, and then divided by, if like we don't do the measurement, and then divided by time. And this one is going to give you the rate of the change of the coherence. So this is like the coherence. This is the coherence for 1 more measurements, and this is the difference between the 2. So, okay, 5 pages of calculations and so on and approximations. It turns out that these functions here is just become something that is like analytically possible, and it's a function of theta, which we can then plot it into this one. And then we find that the optimal theta is around 1.50055, which is kind of like a cool number. It is close to pi and 2, but it's not quite pi and 2. And so this is like kind of an optimized angle that we found. And then we're going to call this regime as like a map-based optimized adaptive algorithm in asymptotic regime, which is like MOAAAR. And we can call it like more. And this is like pictures that we found on the internet. It's kind of quite nice. And then, so here is the result that we found using the data to be that number, that magic number here. And ensure that the decoherence rate is much lower now. And then compare with the theoretical analytical calculations, which is like that gray line here, which comes from the edge functions that I showed you before. Just like kind of plug in a number, and then basically it has the grid agreement between the 2. Okay, so this is like no control. This is the decoherence for the no control. This is the with control, but not optimal. And this one is more like with the optimized angle theta that we found. And we can reduce the decoherence rate with that factors here that related to gamma and then kappa square. All right, I think Kind of like over the time by 15 minutes, and that's the conclusions of my talk. So I talked about the sequential Monte Carlo method techniques for estimating the parameter in the experiments. And then I talked about the spectator system, where we have like spectator qubits next to the qubits that we want to do the noise cancellation. And then I introduced the tool that is called like Moore tool to do the finding the optimal angles and measurements for the spectator systems. Okay, and thank you for your attention. Hoping you guys are still there. I don't hear anything.
Yes, we are still here. Thank you, of course.
Thank you.
This is excellent. Thank you so much for the great talk. And this was really nicely explained. And we had a lot of questions already during the talk. Oh, and Vishal also confirms we are here.
Okay.
We have 3R.
Should I stop sharing, or should I just keep this one on?
I think we can keep it on, or hello.
Okay,
Yeah, we can do all three at the same time.
Sure.
All right, awesome. So I'll leave it to see if there are any final questions from the audience here as we are coming to the close. But I know I've thrown in a few of my own questions already, and I don't know if you had any last sort of big messages you want to share with folks, or conclusions, whether it's from the talk or beyond. This would be also a good time to do that if you'd like. And I think one other thing I should relay from Joshua Combs here, I think Josh, he says, thanks, Areeya, fascinating talk.
Hi, John. Thanks for coming. Yes.
It's good to see you. He says, how did you numerically implement the particle filter? I'd write your own software, or did you? I think he means you'd write your own. Did you write your own software, or did you use a certain package?
Okay. Definitely. These questions would just go to Jason Ralph. So he wrote the codes himself. Yeah.
I see.
From MATLAB. Kind of an old style. Not that old. I shouldn't say that. Yeah, but like MATLAB code. Yes.
Oh, that's good. That's good. Josh says thanks. I think Josh sneaked in some last hour questions as well last week. So big kudos to you, Josh. Joshua comes. Now from Lucas B, what are the advantages of implementing this technique compared to the other state space estimations such as Kalman particle filter?
Oh, that's a good question. Was it advantage of Kalman? Well, in the sense that like using the SMC, which is like the kind of like techniques from Monte Carlo, you can run it with like as any numbers of the number of particles that you want. It could reduce the number of the calculations, or like the computational power. It's like with the Kalman filter, I think it's gonna work harder, because like the more parameters that you don't know, the worse that could get. And with the Monte Carlo, you could kind of like play around with the number of particles, and then how many rounds of doing the resampling, and it would just make the calculations much more doable. And that would be my answer. Yeah.
Can you say a little bit more? Can you remind us how the resampling works again?
So in this case, like resampling, so let me just go into, I did not talk so much about the resampling, but I can kind of touch it. So here, like let's start with, let's say I have some number like 100 particles, and then I start updating the weights until the weight becomes like really large in like these 3 points, and then kind of almost zeros on the rest. And then, so let's say that you only have like 100 points, then you would not sure, or you would not like believe that that 3 points with the high weight would just be 3 values of possible numbers. So at that point, when the number is too small, then the resampling is doing like this, like you kind of like thinking of it as like the weight, so kind of like Gaussian distribution around the 3 points, and then using the Gaussian distribution around that 3 points, and then sampling another 100 points around it in order to explore the parameters around that point with a higher accuracy, and then do it again.
Yeah, that has
so
a
that,
name. I forget what it's called now.
oh yeah. So it's probably there's a name. I'm not sure. Yeah. So
I remember
right.
that with simulating quantum trajectories for something else. But anyway, side story.
Right. So that's like the techniques in the resampling, and there's a lot of details into like how big of the variance that you would get, that you would choose, and what about other points that has like a smaller weight. You would have to do the Gaussian distribution around it as well, but then you would have to do like less probability on that point, and then more probability on this point, and so on. So I think it's really, well, I mean, so far that I talk with Jason, it's more like kind of intuition based, like, okay, let's just do 10% of these and 90% of that. And then, yes, it works. It doesn't have like a really like fixed numbers in terms of how to do the resampling.
Yeah, and for your initial lambda 0 particles, or sorry, for your initial set of W's, I guess, right? For the example that you gave to us later with the Rabi frequency and all this stuff, I mean, you sample from some Gaussian distribution initially, or how? What do you? It's not
just
right.
Initially, it would just be a uniform distribution, definitely.
But like the Rabi rate could go from 0 to infinity, right? So
that's right. But it will be uniform during like some value. Yeah, you're right.
Yeah, uniform and some bound, I guess. Okay.
It will be some bound. That's right. Like we know that it's not gonna go above what 20. Is a 20 is too high? Yeah. So
okay, so you pick some
something like that.
relevant.
Relevant, exactly. Yeah. That's right.
I see. Okay, and then for each of those particles, you sort of track the evolution and keep the update until you get to the step here.
Right. So this is kind of like the combinations of the state estimation. Well, not sure if I can call it state estimation. It's like a calculation of the state of the qubit or the systems at the same time as the parameter estimation. So that's the techniques.
Yeah, and then some of them diverge a lot from the sort of realized experimental data.
Right. Yeah. Mm-hmm.
And, can you remind me how you measure? Maybe now just forgot you mentioned this already. How you measure the distance, so to speak, between those two?
Distance between those two. What was the distance?
Sorry. Between the agreement for a set of parameters and the.
Oh, you mean like that result?
Mm-hmm.
No. Yeah. Okay. Wait. So like, I think I'm not sure. Do you want to finish? I think I interrupt your questions.
If you go to the next slide.
Yeah.
Okay, yeah. So there we go. That's better. Yes, thank you, Paul. So on this slide, you start off with say 100 particles.
Yeah.
And which basically means that you have a set of weights for tau, for eta, for omega, and so on.
Mm-hmm.
And, for x of 0, just the stuff that's in the red box.
Mm-hmm.
And so for each of those trajectories, for each of the particles, you have a set of trajectories that and a set of estimations based on the measurement record wise, which gives you sort of an ensemble of density matrices at the end or over the time of it.
Right.
could we in some set, like, how do we measure now the closeness between one of those sample points and the experiment in a sense? Like, can we say something about that?
Okay. I think so. I think you kind of have a pictures of the state, like in your mind. I think in terms of like quantum trajectories, right? But I want to switch that picture into looking at the parameter space. So the state in this way is just a tool to help you calculate the probability of the measurement record. So that to me is just like the part that is useful for the SMC, because like the state is the model that will tell you what's the probability of the record. It depends on the state at that point. Yeah. So once you have this one, then you can just think of how the weight is changing in time from like before where there's no information at all, and then after when you start like updating your weight depending on the measurement outcome that comes in. And then when then the estimated parameters will comes into like calculating the mean of this using all the weights that we had. Like for example, like just using something like this. Well, once we have the weights, then we can find the mean of the parameters that we want from there. Does it make sense?
Yeah, I think you're saying that the density matrix here is very intermediate step. It's a very intermediate result. And then the thing you care about is how blue those dots are, which represents the probability that parameter evolution under these would have given that result.
Yes, that's right. I mean, there could be a good questions of like how would it look like in terms of like the ensemble of trajectories, but I would just think that if the parameters are like really close together, then the trajectory would just be like along the same lines or like in the same trend and so on. Yeah. Mm-hmm.
Yeah, this is very operational in that sense, which is kind of nice.
Right. Yep.
Good. I think we are coming up at the extra half-hour mark, so I think we've probably kept you up late enough in Bangkok, Thailand.
Sure.
So I think
I'm surprised that like there's not much of the questions that related to the spectator qubits. Maybe it's just too complicated.
I think it's very elegant, and also the first part is, I think, quite catchy in of itself too. So,
yeah.
I think I can say for the audience here, there are a few comments you'll see in the chat later, like great talk, thank you for the response. So I think I'd like to thank you and the audience at this point for tuning in to the Friday Live Qiskit seminar series.
Thank you for the invitations and for doing this. Yep, as well.
Yeah, thank you, Areeya. It's been a real pleasure. And folks, you can go back and watch this talk. And otherwise, we will see you next week, Friday at noon Eastern Time. Thank you, Areeya. Thank you, everyone.
Thank you. Have a good night and good day.